Okay, our next speaker is Kevin Byrne, who's Chief Geoscientist at VRIFY, with a strong academic foundation specialising in integrated multidisciplinary data to enhance mineral discovery and ore body characterisation. His work focuses on leveraging diverse geological, geophysical and geochemical insights to improve exploration efficiency and decision-making. With experience spanning research and applied geoscience, Kevin brings a rigorous data-driven approach to understanding subsurface systems and advancing exploration outcomes for mining projects. So please join me in welcoming Kevin.
Thank you. Thank you, Clyde. That must have been ChatGPT that wrote that, because I'm not sure I did that. So I'm going to start with just a little cautionary statement. I'm going to throw a lot of statistics at you, so I'm going to hope you're all suitably skeptical at the start. But what I'm trying to do is paint a picture of the current exploration environment that AI has emerged into, the trends. And I'm going to show you some results from a survey that VRIFY conducted with ISPOS. And I'm going to show you a case study, a very practical application of AI in a mature exploration district, that's Woodjam in BC. So a big thank you to my co-authors here from Vizsla Copper. Okay, so most of us are aware, discovery rates are down 50% over the last 20 years or so, between 2005 and 2024. And that's across all deposit types. Probably a little flatter for copper, depending on who you ask. So discovery rates down. I found this one really interesting. Juniors are making more discoveries than ever before. That's up 100% over the same time period, from 40 to 80%. So that's who's out there making a lot of discoveries. Majors love the brownfields. And this probably makes sense. It's a winning strategy to look for mineralization where you already know there's mineralization. There's probably some cost savings in exploring in mature and brownfield environments as well. And it demonstrably works. So I'll pull this out of another shoddy report, but looking at the pre-mining level resources in Circum-Pacific region deposits, pre-mine levels 1985 through to 2018, increase of 200%. Now, not all that is going to be economic, but we're finding, in this case, more copper around where we know there's copper. That obviously does not detract from, brand new greenfield tier 1 discoveries. They are incredible value makers, but this is what is happening. This is where, in this case, where copper resources are actually coming from. Down 40%. That's the number of greenfield copper projects drill tested in 2022 through to 2024. And this is mirroring the longer term trends in where capital is going into greenfields exploration. So in the early 90s to 2000s, 50 to 60% of exploration budgets was going into more immature greenfield environments. And this is the pattern for copper over the long term. Okay, similar story for gold here. Gold discoveries and inventory growth since 2020 has mostly come from brownfields. The new discoveries that have been made are smaller than in the prior decades, mostly that sort of sub 5 million ounces, tier 2-ish, and there's fewer of them than in the preceding decades. So the picture I'm painting here is we're not doing as well as we used to. We know why. There's dealing more with challenges with cover. A lot of the outcropping systems have been walked over. So demonstrating here, similar to copper, the gold growth that has come is coming from brownfield environments, 100% increase in the resources from 1985 levels, pre-mining levels, through to 2018. So it's working to explore in brownfields. Okay, so in parallel with decreasing rates is the increasing discovery costs, and this is all 2024 equivalent dollars, up 230%. I think Shadi makes an interesting sort of subjective comment in the SEG newsletter article about the quality of the targets has decreased. Now it's hard to sort of pin down exactly what this means, but I think it probably relates to increasing cover, exploring blind targets. They're higher risk targets, as well as the experience level, both organizational and individual experience level. Have we lost that sort of tacit knowledge of what it feels like when you're on the brink of discovery? This is what they're attributing to the sort of increasing costs, as well as just, in general increase in exploration costs, inflation. Okay, so this is one probably everyone's similarly familiar with, but 14 years to make a discovery. And there's this danger of averages. Some are much faster, some are much longer. But an interesting metric, I think, is that it's 2.7 companies. So a lot of juniors are out there looking for projects that haven't seen too many operators over the years for lots of reasons, often above ground challenges. Yeah, so 2.7 companies to make that discovery, and then 3 years from that last company. So it's not like they arrive on the ground to make a discovery. They still have to work it, sweat the project, and really be thoughtful about their exploration activities. So exploration spend, we're up 20% from 2005 to 2024. I think we can probably anticipate it's going to be a good year this year and probably even better next year based on current commodity cycle and prices. But we're still down from the lofty days of 2012. So overall, the spend is lower. Okay, so that's the environment. Now let's think about sort of targeting as a whole in mineral exploration. This is a little simplified, but targeting 4.0, what does VRIFY mean by that? There was the days of manual mapping and prospecting, just walking around, looking for visual mineralization. Works great. Then came the geochemical and geophysical surveys, allow you to explore broader areas more rapidly. And then sort of with that came the digitization. 3D mapping, GIS, particularly GPS, I think, really sort of changed how we were exploring. And now I'm suggesting here we are targeting 4.0 at the age of AI, ML tools in exploration. But there's some nuance here. Again, from one of the shoddy reports and others, but if you look in detail at some of the technological evolution, tools that we're using in our industry, it's pretty consistent, steady stream of new technology. And the observation is it takes about 10 years for that piece of technology to become mainstream. Call out here at the bottom, we have in the geophysics row, currently it's muon tomography and ambient noise tomography. They're the sort of some of the newer tools around. But at the top here, sort of grouped together, enabling technologies. And this is why I think the next leap won't come from a new survey type. It'll come from a more agnostic system that can combine all these data sets and look for the patterns in a way that humans haven't been able to do quite the same before. And I'll call out here, Leapfrog. So around 2003, Leapfrog, Iran's released Leapfrog. Probably 10 years later, it became, I think, mass adoption, mainstream. Everybody was using it and saw the benefits. Iogas as well, I think was probably, I know for me personally, it changed how I thought about geochemical data and how I worked with it. And it was, 6 years maybe from original to sort of everybody using it. And I'm suggesting here we're somewhere at the start of this. It's not clear what tool and what exactly it's going to look like, but we're at this incipient stage. Okay, so VRIFY conducted a survey along with ISPOS and another independent sort of survey type person. There was 135 self-selected respondents, so there's some people decided that they're going to respond. But this is what they said. They're all from the exploration mining industry. They do have that in common. So frequency of AI usage, 21% most of the time, 36% some of the time, 31% rarely, and 10% never. So we are using these tools. How much of it is just sort of like we saw earlier from Tyler about whether it's Gemini or Claude or GPT, we're starting to use some of these tools to increase our productivity. But how systematically are we using them for answering exploration questions or testing hypotheses with your exploration data sets? Of the respondents, 78% of them said that part of their job was involving AI evaluation. So, it's a common theme. People are scanning the industry and seeing what's out there. So people are thinking about our community is thinking about these things and how they should be applied to their business and problems. In terms of spend, I think this one's revealing. So 52% of respondents say less than 10% of their budget is sort of AI related for exploration. So still relatively underutilized tools. 4%, don't know which client or which company that is, but 4% are greater than 50% of their budgets. So this is how the money's been spent currently. Groups most skeptical of AI, and I include myself in this. And I am a skeptic, very much so. Geologists are obviously the most skeptical. Site, field managers, people involved in execution, less so. And then, of course, the executives, the accountants and engineers making the decisions are the least informed and least skeptical. So that's reassuring. No offense to anyone. But we should be skeptical because we are the domain experts, and we have to work with data scientists combining these two different fields, asking the right questions. That's been a theme a lot of people have mentioned. Okay, so our survey says, well, what are people trying to achieve with their technology goals? What are they actually trying to do? AI mineral targeting was identified, database upgrades, and cloud-based geoscience tools. This is what our community is saying, the 135 respondents. This is what they're saying they want. Top 10 reasons for adopting AI tools. Competitive advantage. Now, whether that's reality or perceived, that's TBD. But faster target generation, so getting to decisions faster. I'm going to touch on this, and that was something I think Tyler mentioned as well. Getting decisions faster. Reduce risk. Risk of drilling dusters. Risk of making the wrong exploration decision. This is what we're trying to do with some of this new technology. I love this one. So it's a lot like our opinions of our own driving. 50%, or is it? We all think we're better than average drivers, right? This is similarly. So 78% of respondents think that their own organization is keeping up with the innovation, but less than 50% think the industry is as a whole. So there's a gap, a perceptions gap there. Okay, so risks. That was in the title. I better talk about the risks. So I think the risks relate to a misalignment of expectations of outcome. What somebody's trying to achieve with AI or ML tool, and a misalignment of that with respect to the available data, coverage, resolution, and richness. It's how those two things meet. And this again relates to what are you trying to achieve, what questions are you trying to ask. Cultural risks, and this is probably the bigger one. There was a 2025 Cornell study that says there's often a gap between an organization's commitment to innovation and then its structural ability to deliver it and sustain it. So we want to do it, but can we do it? Other cultural aspects, the size of the organization has a big impact. Smaller groups may not have that sort of knowledge, depth, and breadth, but bigger companies may be sort of paralyzed by indecision and inefficient decision making. So business perspective and the other risk. Throughout another little McKinsey report last year, 80% of large corporations have tried some sort of AI productivity boost internally, but only about 80% of that 80% think they were getting a material ROI return. So that's a risk that we're going to spend more money on these things and not get a return on them. I don't have answers for all this, by the way. Just okay. So the opportunities. Well, I think the opportunities relate to the data itself. AI and ML lends itself to data rich. Now, brownfields and mature jurisdictions are where we have a lot of data. It's also where we are demonstrably exploring the most and where most of the resources are going. So for now, I think the opportunity is in these data-rich environments. That doesn't mean greenfields isn't worthwhile. It's just, I think it's a harder problem to solve, is the truly generative global scale AI type targeting. But for now, the opportunity is in the brownfields, in the data-rich environment. Business needs. So we want to get to an answer faster. We want to reduce risk. Really want to sweat the targets and be confident before you set in motion permitting cycles and exploration programs. Are you collecting the right information to try and reduce the uncertainty on your targets? And to me, the biggest opportunity is really the collaborative piece. So we are the subject matter experts. We know the mineral systems. We know how we think they express in all the different data sets, but we are not familiar enough with all the algorithms and possibilities coming from the data scientists and the AI guys. So this is the collaborative part. It can't just be one sort of group working on these problems in isolation. So I really believe in that collaborative piece. Okay, so I'll show you a real life example with one of VRIFY's clients. So for those who are not familiar, Woodjam, it's sort of central BC. It's Quesnel Triassic Arc, known for porphyry copper, moly, and epithermal systems. It's this particular district is quite data rich, but there has some challenges. It has both sort of young volcanic cover as well as glacial till cover. So it does have some exploration challenges. And what VISLA wanted to achieve in their Woodjam district was a more systematic review with new tools and new perspectives. What else is there under cover? Can we try tease out some new targets that they hadn't seen before? I sort of mentioned some of this, but yeah, Woodjam shown, get fancy here. Here's the Woodjam district. Several sort of, here's Mount Polly, another little porphyry center here, and an epithermal gold system at red gold. So there's a sort of north-northwest trending belt of nickel volcanics that sit sort of on the margins of the Tacumcane batholith. And we just have a sort of a little bit of a country rock that sits up above that intrusive contact. So, you know, good place to form a porphyry. But there's cover. This brown material here is the Chilcotin basalts. And I think the green stuff here is the till cover. So part of the property is actually the till extends up here, is covered. Okay. So the workflow at VRIFY is, you know, I'm going to show you a data stack. We build up the data stack, the regional and property scale data, or rasterize everything. The workflow is to start regional, so start big zoomed out using gravity, using magnetics, try understand the regional scale controls on the localization of the known systems. And then we'll go to property scale, work with the more local data. Geophysics underpins a lot of the modeling that we're doing. And then we tend to add in the geology, rerun, iterate, and then add in a lot of the surface geochem and rerun. The idea is you're iterating, testing hypotheses, not going out and testing them in the field straight away, but you're testing your ideas. I think this layer and that and this distance from this intrusion are going to be the right combination. Let's see how that statistically holds up against the knowns. So we do multiple target iterations to produce a more probabilistic prospectivity map or heat map. And then we compare these different iterations and look for coincident targets at different scales. That's the sort of the framework that we're applying. So here's Woodjam, getting to the fun 3D stuff. Here are the known porphyry centers and their property outline. It's good road access there. So we'll zoom in. I mentioned some of this, but there's at least 6 porphyry centers. They have different sort of host rock as well as different mineralization style, different magmatic affinities. So they don't all have the exact same sort of footprint. Some copper gold, some copper moly. But this is like our sort of our knowns. I mentioned some of the geology here. I think what's interesting about this region is, you know, overall, the rocks in this part of the belt are trending north-northwest, but locally here in Woodjam, we see the sort of the bottom of the Nicola volcanics, and it sort of goes up fascies to the north, trending more northeast. And on some of the interpretive maps, but not all of them, there's some dashed faults like this. So where I'm going with this is we were really interested in what was maybe controlling the distribution of the volcanics here. Is there perhaps a unmapped or not well-mapped graben or half graben? Can we tease that out with some of the magnetics, some lineaments and things like that? That was our question, was what's controlling the elongate direction of mineralization at these porphyry centers. Yeah, so here's the basaltic cover. And then, as I mentioned, there's sort of till all through the southern part. All right. So we have a hypothesis. We sort of want to understand the structural controls. What we do is we build our data stack. And what that means is our strategy is really to rasterize everything. I'm going to show you we're using a thing called a vision transformer, but it's a 2D vision transformer, but we're making sort of 2.5D indicative depth text to targets from this using this vision transformer. But what we do, let's say we have our geology, we will create distance from maps. So distance from a certain polyline, distance from a certain unit. And we'll rasterize the ages of the rocks or the rock units themselves. The other thing we'll do is fault disturbance maps. So using the known mapped fault orientations, propagate sort of a seismic wave through it, and then model what are the potential deformation zones around inflections and intersections. So that would be, disturbance. So as you know, geochemistry is a challenge. It's discrete, heterogeneously distributed data. What VRIFY are doing, and there's lots of other people who have tried this, but we link the point data to all the secondary data, all the auxiliary layers, remote sensing, topographic features, catchments, obviously, and the underlying geophysics. And what we produce are geochemical response maps that are predicting the geochem response between the measured samples. But it allows you to have a continuous data set, which is what vision transformers need for the data to be interpretable. And then we'll do things like anomaly maps. So then we stack up all the multi-element data, organize it by lithophile or whatever combinations you want, and we'll make anomaly maps. What's the most anomalous? As I mentioned, the geophysics, geophysics really underpins everything, in my opinion. I really stretch the DEM a lot. We do, first vertical derivatives of DEM, but the geophysics underlies a lot of the predictive power of this sort of targeting workflow. And we'll take all the standard Fourier filters and we'll run additional sort of vision transformer things like ResNet. And we'll do some traditional stuff like Harlech. And what it's about is enhancing that signal. So taking those data sets, whether it's regional or property scale, and really trying to look for the more subtle signals. And lineaments. So we're doing a more automated and objective lineament analysis on, say, a first vertical derivative of the mag. So I'll show you what that looks like. So I mentioned this, but this is one of the things we did at WoodJam. We take an input survey. We're using pixel edge detection. There's a few different levers we can pull with respect to the sort of the wavelength of the line and the gaps between the lines. But we produce a lineament density map. As I mentioned, can search different orientations. And then we sort of produce a heat map of the lineament density through sort of Gaussian filters. And what we end up with, so here's an example of a RTP, but I wanted to see more potential arc parallel lineaments. So I'm not saying structures. Some of them are going to be structures, some of them are going to be lith contacts, but they're fabrics in that data set. And we can see here where the known deposits sit. And we make a heat map of that. But I also was really interested in the potentially cross-arc or arc-oblique type structures that were sort of sub-parallel to the known trends at these deposits at WoodJam. And where it gets interesting and powerful then is, here's the Chilcotin, here's this post-mineral cover. And you can see we are extrapolating potential favorable structures under the cover, which you maybe couldn't have done beforehand. And make complexity heat maps of that. So then we take all the layers you want to use, the geology, distance from faults, a lot of the data augmentation, that signal enhanced layers. And that's our data stack, our sort of input features to the model. Next step relates to what we call learning points. This is where we're using the knowns. We're learning by inference. In this case, we're looking at drill holes and outcrop where it is, I'm going to show you a screen grab, where it is greater than 1,000 ppm and greater than 1,000 ppm copper and greater than 0.1 gold. This is a screen grab from Dora. This is our cloud-hosted web browser accessed online targeting platform. And this is where we're setting up the learning points. So we're setting up a classification here. We're telling the machine that this is the target, and then we've given it what layers we want it to work with. And it's going to go look for that known pattern in the unknown areas where you don't have any drill holes or samples. Okay, so next step it relates to the vision transformer. And the vision transformer uses the same sort of underlying architecture as the large language models, but rather than linearly embedding the words, it patches up the images. And it does it in a smart, sophisticated way that I can't fully explain. I have to lean on an AI expert for that. But what it's doing is data fusion, smart data fusion. It's taking all these layers, like real geology, geochemistry, and geophysics, and bringing it together to look for that multi-parameter signal. We handle inversions. We take slices through inversions. So if we're doing simulations of inversions looking at residuals, we could take the P25, the P50, the P75, input those, run an experiment, and compare and contrast. See what happens when you use a different iteration of the inversion. So here we pass all the data through the vision transformer and output an embedded image. And this is the computer vision's interpretation of that data stack. And then what we do is we relink to the learning points and run multiple simulations of, is it mineralized or unmineralized? And what we output is this. It's a prospectivity grid where the warmer colors are higher prospectivity, higher probability, and the cooler colors are lower prospectivity. And then we can filter those to look at the higher probability points. So this is what we're seeing here, filtered to, I think, probably greater than 70%. And if I zoom in here and move it around. So what we can see is some high probability areas, and some of these are at the knowns, but there are some other targets here that are at the unknowns. And this is where it gets interesting, right? So what's happening here is we've taken the data stack, the vision transformers fused the data, and then what we're doing is going, okay, where else is that pattern? Where else is there a high probability of the known pattern occurring elsewhere in the area of interest? And that would be things like this. So here and here, where it has not been drill tested and not been fully explored, they become the targets. Obviously, it's important for things to be explainable, more transparency. So more glass box, less black box. What we do is we run feature importance plot over the model, and then we're able to sort of report out what are the most impactful layers for that specific model. In this case, it's the tilt derivative, some of the till geochemistry, some of the local tilt from a more high-resolution survey, and on down through the list, you can see how the different layers are interacting, combining to characterize the known mineralization. Okay, so last slide, wrapping it up. What do we know? AI has sort of emerged in exploration. Not because we've suddenly become digital, but because our traditional workflows have been underperforming on average. And they're underperforming in a sort of environment of rising costs and constrained capital. What our community is trying to achieve with AI is a competitive edge, faster targeting, and reduced risk of failure. So this is where I believe AI is a good solution for many of these challenges. AI doesn't reduce geological uncertainty, but it does reduce that decision latency and reduces inconsistency with the uncertainty. So that's it. Thank you very much to IMDEX for the invite. Cheers.